The objective of this experiment is to load a tensile test sample at a constant crosshead speed until failure, while recording the value of the load and the change in length of the test sample at each stage. Then, based on the collected data, stress-strain relationship will be obtained. Modulus of elasticity, yield strength, ultimate tensile strength, yield strain, failure strength and strain to failure will be determined. The strain will be measured by using a video extensometer. In addition, the reduction of cross-sectional area of the tested sample will be determined. There are basically three types of strain measurement methods: mechanical, video and laser type extensometers. In this experiment, a video type extensometer will be used to measure strain under a known load. In real life, there are many factors involved in the nature in which loads are applied on a material. These are some common examples of modes in which loads might be applied: tensile, compressive, and shear. The stress is calculated by dividing the amount of force applied by the machine in the axial direction by its cross-sectional area, which is measured prior to running the experiment. The strain, which has no units, can be calculated using the equation below, where L is the instantaneous length of the specimen and L0 is the initial length. A typical stress-strain curve would look like as in the figure. In reality, not all stress-strain curves perfectly resemble the one shown here. This stress-strain curve is typical for ductile metallic elements. Another thing to take note is that the figure shows an engineering stress-strain curve. When a material reaches its ultimate stress strength of the stress-strain curve, its cross-sectional area reduces dramatically, a term known as necking. As the computer software plots the stress-strain curve, it assumes that the cross-sectional area stays constant throughout the experiment, even during necking, therefore causing the curve to slope down. The true stress-strain curve could be constructed directly by installing a gauge, which measures the change in the cross-sectional area of the specimen throughout the experiment. The true stress-strain curve could be constructed by assuming that the volume of the material stays the same. Using this concept, both the true stress and the true strain could be calculated using these two equations. The figure also shows that a stress-strain curve is divided into four regions: elastic, yielding, strain hardening, and necking. The area under the curve represents the amount of energy needed to accomplish each of these events. The total area under the curve, up to the point of fracture, is also known as the modulus of toughness. This represents the amount of energy needed to break the sample. The area under the linear region of the curve is known as the modulus of resilience. This represents the minimum amount of energy needed to deform the sample. The linear region of the curve, which is called the elastic region, is the region where a material behaves elastically. The material will return to its original shape when a force is released while the material is in its elastic region. These are typical stress-strain curves of polymers. The figure shows that materials that are hard and brittle do not deform very much before breaking and have very steep elastic moduli. The following equipments will be used during the experiment: Universal Testing Machine, a computer with trapezium software, a video extensometer, a caliper. Flat, or circular, plastic or steel with various dimensions could be used. In the experiment, PVC and high-density polyethylene, HDPE, polymer samples will be tested for tensile test properties. Now, we are ready to carry out the experiment. We have to position the upper jaw in order to place the specimen. we are going to clamp both tips of the specimen.
Okay.
Since the extensometer tracks the clips, we have to place them on the shaft of the specimen at an upper and a lower position. Here, we have to adjust these rectangular objects on the interface, in order to increase the sight of the extensometer. The bars below show the levels of tracking capability for the camera. After calibrating and zeroing the force, and other entities, the test sequence can begin. Earlier trials with HDP showed that the extension of the specimen would exceed the limits of the test equipment. Therefore, after some time, test sequence is ended manually. The data is collected as an Excel sheet which can be used to calculate the required entities.